Welcome to Lesson 15D, More Particle Statistics. I'm going to introduce and define 4 more statistics, these 4 listed here. And for each one, I'm going to use the same example sample that we had in the 2 previous lessons as an example. I probably don't need to say this anymore, but make sure you can duplicate my results for this example sample, and then you should have no trouble on quizzes and homeworks. The first one is called DPAM, arithmetic mean diameter. For each of these cases, I'm going to show you how we do it with listed data and then with group data. For listed data, this is just a simple average. We add up all the particle diameters and divide by the total number. In all these equations, remember, I'm using I when you have listed data, but I use J when we have bins or groups or classes. Let's call this DPAM number, a number in parentheses because we're doing a number distribution here in this example. If we were doing a mass distribution instead, we would call this DPAM mass. How do we calculate an average with group data? We don't have all these DPIs. All we have is DPJ, the middle value, and we know the number of particles. So for lack of better information, we approximate that each particle in bin J has a diameter that's DPJ, which is the middle value. That's really the best we can do with group data because we don't have all the detailed information. This is the key for how we will calculate all 4 of these guys up here because we know these values with listed data and then we modify for group data like we just did here. So you can see how this works. If there's 10 particles in bin 1, for example, we assume that all 10 of those have diameter DPJ. So this is just 10 times DPJ, which would be adding up 10 DPJs basically. Then we add up all the bins. So you can see that this is a grouped data version of the listed data. Now, for each one of these 4 statistics that I'm going to define, I will also do example calculations using our example sample. I used Excel for all this. You can use whatever you want. I list only 3 of the columns, J, DPJ, the middle value, and the frequency, the NJ, which is the number of particles in each bin. I made a column called NJ DPJ. This is to calculate DPAM. And let's check this first row. NJ is 104 and DPJ is 2.5, and that gives me 260. In Excel, I'd fill that down for all the rows, and then I'd sum all of these. If you have a bin with 0 in it, it doesn't add anything to the sum, so we could just leave it there. Then from this equation, I write DPAM is 1 over 1,000, that's our NT, times this sum that we just got, I get 11.23 microns. I'll give my answers to 4 digits for all of these. Of course, Excel will have many more digits than that. The median diameter was 9.0 microns for this particular example sample. So DPAM does not equal DP50. In fact, DPAM is greater than DP50, and that's pretty typical for log-normal distributions. Why? Because it's not symmetric. If we had a Gaussian distribution, DPAM and DP50 would be the same. But since we have a skewed PDF, it's not symmetric. It turns out that DPAM is greater than DP50. Now let's define geometric mean diameter. I'll call this DPGM instead of DPAM. For listed data, if we have all the DPs, it's like an average, except we take a product instead of a sigma. We use this capital pi, and then we take the whole thing instead of just dividing by NT, we take an exponent 1 over NT. So for listed data, we just put in all our diameters, multiply them all together, and then raise that to the 1 over NT. Again, we translate this to group data using our approximation that all particles in the bin have the diameter DPJ. For example, if, say, the first 3 particles here are in bin 1, we'd take that first bin with the diameter DP1 in the middle and raise it to exponent N1, which in our little example would be 3. And then we move to the next bin, and you just keep doing that. So this is how we get group data with the same equation. In other words, for each bin, we have DPJ times DPJ times DPJ, NJ times, or DPJ to the NJ. Then we multiply that for each bin and then raise the whole thing to 1 over NT. Now here's an exercise for a long, cold, rainy night. If it's a log-normal distribution, this equation can also be written as this equation with an exponent and natural log. Now, before I continue, I have to make a note here. It's not really proper to take natural log of DPJ when DPJ has units in microns. All the books do this, but our mathematician friends would cringe if they saw that. So what we really mean, although we won't write this out, but keep in the back of your mind, natural log of dpj divided by 1 micron, where dpj has to be also in microns. So we'll always write this, but we really mean this so that we get no units in the natural log. All right, let's try both of these equations, this one and this one, for our example sample. In Excel, I took dpj to the nj for this definition up here, and you get these huge exponents. In fact, when you take these and then you try to multiply them all together, this is a product. By the way, in Excel, you can call this product and then put all these cells in here. But Excel barfs. It can't handle such huge exponents. So that doesn't really work. I actually proved to myself that it does work if I put in much smaller numbers of particles in each bin so that these numbers aren't so huge. And I do get the correct answer. But here, we're not going to be able to do it. So let's do the other equation here. I made 2 more columns, natural log of dpj, of course, meaning this, and then nj times natural log of dpj so that I could sum those. And we can verify, take the natural log of 2.5, we get that, and then multiply that by nj, which is 104, and I get 95.29. And in Excel, you fill that down, and then we just sum everything up in that column. And then dpgm from our equation here is exp 1 over nt, which is 1,000, times this sum 2195.18, and I get 8.982 microns as my answer. Theoretically, dpgm equals dp50 for a log normal distribution. For our example sample, dp50 was 9.0 microns. So these are pretty darn close, which means that this distribution is very close to log normal. Otherwise, these two would be much further apart. There's always a little bit of scatter in any kind of data. Now let's look at standard deviation, which we call sigma. This is the sigma for listed data that you know and love from your statistics class. You can read why this is nt minus 1 instead of nt. You should all be familiar with that equation. Again, we translate this to group data by making our assumption again, the same one we've been doing, and I just found a mistake. This should be nj, not nt. We have dpj minus dpam, and we have nj of those for each bin, and then we just sum up from 1 to j. For our example sample, I added another row here. I happen to do dpam minus dpj instead of dpj minus dpam. Doesn't matter since it's squared. So let's check this one. I have nj times dpam, which we had up here. I'm giving a few more digits to avoid round off error. So there's our nj, here's our dpj, and squared. I get 7921, which agrees with this value. Again, fill that down and sum them up. And then let's plug in our equation for sigma. I get 7.930 microns. Sigma has the same units as the variable when you do statistics. Now let's introduce something called geometric standard deviation. The notation is sigma sub g. You probably never saw this one. It's for log normal distributions. We do all the statistics exactly the same way as previously, but we use natural log of dp instead of dp as our variable. Again, that means dpj over 1 micron. That lets our mathematician buddies sleep at night. If we wanted to do this for listed data, we would first define an arithmetic mean of natural log dp. We use the same equation we had before. It's a simple average, but it's an average of log dp rather than dp itself. And then we define sigma the same way, except now it's a natural log of sigma g. And then this is the same equation we had for standard deviation, except again, we're using natural logs instead of the dp itself. For group data, we make our approximation again that we've been doing. Instead of summing all these, we have nj times the natural log of dpj for each bin, and we sum over j bins. So this is ln dp, am, and then we define our natural log of sigma g as this using that same approximation. And then finally, we want sigma g itself. So sigma g is just exponent of ln sigma g. Here's a caution. The arithmetic mean of natural log of dp is not equal to the natural log of dpam. You're tempted to do that, but instead we have to go through this calculation. So let's do it for our example sample. We already had these 2 rows in a previous page, natural log of dpj and then nj times that. So first we have to calculate natural log of dp, the arithmetic mean, from up here. So we'll do that first. It's the sum of all these guys, nj natural log dpj, that's this, divided by nt. Now I use that in this column. So we have nj for the first row here, 104, times 2.1952, which is natural log dpam, which we just calculated, minus natural log dpj, which for this row is 0.916 squared, I get 170.1, which agrees with this. Fill that down, sum it all up, and then we use that with this equation. This whole numerator here is that sum we just calculated. We just want to take that divided by nt minus 1 and then take the square root. So natural log of sigma g is square root of 459.04 over 999, which is nt minus 1. I get 0.6779 to 4 digits. And then finally, sigma g itself is exp of this guy, and I get sigma g is 1.970 microns. So that's all 4 of these statistics. Make sure you can duplicate my numbers before you try any quizzes or homework. Now I'll just do some comments. The first one is, why are we doing this? Why are sigma g and dpgm important? You may recall from statistics class that we can characterize any normal or Gaussian distribution by 2 parameters, namely sigma and dpam. Well, it turns out that we can also characterize any log normal distribution by 2 parameters, sigma g and dpgm. It turns out also that for log normal distributions, dpgm is equal to dp50, which was our median particle diameter. This guy is very easy to find because that just means half the particles are bigger than it and half the particles are smaller than it. So as long as it's a log normal distribution, once we find dp50, we know dpgm. Recall that I found dpgm was 8.982, whereas dp50 was 9.0 for our example sample. And that's really close, which means that this sample distribution is indeed log normal. There's 2 more special diameters also. You may recall from your statistics class that we often used 2 sigma as a measurement when you're 2 sigma away or 3 sigma away from the mean. Well, with air pollution, we're not that accurate, so we use 1 natural log of sigma g away from the median. It turns out that the cumulative distribution function, which we defined before, capital F of dp, is 15.9% and 84.1% respectively for minus or plus 1 log sigma g. Just like we defined dp50 as the diameter where f of dp is 50%, now we use these 2 other kind of special diameters. We define dp 15.9 as the diameter where f is 15.9%. and dp 84.1 as the diameter where f is 84.1%. And you'll see these 3 diameters as kind of special ones that pop up in a lot of equations in air pollution statistics. This is only good for log normal, which is all that we'll talk about in this course. Let me just explain this graphically. Let's plot our PDF on a log scale, or in fact, what we'll actually do is plot natural log of dp for a log normal distribution. If we plot natural log of dp on the x-axis, we get a Gaussian shape. It's symmetric. The center value is natural log of dp50 or natural log of dpgm, since those 2 are the same. If we go to the left, natural log sigma g, it turns out that this area is 15.9%. That's why this point on the scale is natural log of dp 15.9. Similarly, if we go to the right, 1 geometric standard deviation from the middle, this area is also 15.9%, but the cumulative distribution function is the entire area up to that point. In other words, it's this entire area here, and that blue area is 84.1%. This location here is natural log of dp 84.1. If you add 84.1 and 15.9, the blue and the green areas here, you get 100%, which you have to because the area under any PDF has to be 100% or 1. So that's kind of cool, and I hope it helps explain some of these statistics. Once we have these, we can calculate dp 15.9 is exp of the natural log of dp 15.9 and do the same for 84.1. Now we have our 2 new special diameters. And then finally, there's some relationships between geometric standard deviation and these 3 special diameters, and that's given by this equation. And I'm not going to show it here, but I verified that those are very close to each other when you do this with our example sample. So that's a lot of new statistics that people in the air pollution business use all the time. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.